Okay, so off we go. Last time we were talking about double integrals and iterated integrals and all that. So we're going to entertain now the sort of the natural next question, and that is, what if the domain is not a rectangle? And let me first address the question of how could it be not a rectangle? What is this scenario we're considering? Well, notice that every application that we saw in the past, and I like this picture here just because it's easier to visualize. Of course, I've talked at length about how, this is really not the best picture to have in your mind when you're thinking about a double integral because it's sort of geometrically convenient, but a little bit of a peculiarity. Anyway, lots and lots of applications, and yet all of the applications we looked at, the domain has been a rectangle. So that's what we're going to be trying to broaden at this point, is entertain, what if we have cases, for example, that look like this? What if this is what my loaf of bread looks like? I might want to compute the volume of this loaf of bread. Not all bread has rectangular footprints, right? So what do you do, and how can you do this? And do we have to set up a whole new machinery in order to do this? And the good news is no, it's almost exactly the same. Practically every aspect of it is just literally identical. There's one little difference that we have to worry about. So it remains that we'll be looking for a range of values of y, as y goes from C to D. We'll be looking at individual little slices of bread, as I like to call them. These little slices, it remains, will be cross-sectional area times thickness, just like in the previous case. It remains that those cross-sectional areas will be areas under a curve. It remains that that curve is a graph. It remains that we compute that cross-sectional area with an inside integral. All that's exactly the same. The only difference is that in this case, when we have a non-rectangular domain, the bounds here, showing the range of values of our inside variable, in this case x, those bounds will not be constants. So let me zoom in so we can get a closer look here. Now you can see that for the pictured value of y, somewhere between C and D, for that value of y, my cross-sectional area that I'm interested in is an integral that takes place on that interval, you might say. You can see from the picture, right? Thus giving us this starting value and this ending value for x. Okay, well, yeah, sure, right, fine. But if I were to look at a different value of y, let's say some value about right there, for that value of y, we're looking at, let's see if I can draw a halfway decent representation. My little slice of bread, as it were, is a tall, skinny slice of bread. I don't know, something like that. And you can see right here in the picture that the starting value is a different value of x, right? And likewise, the ending value is a different value of x than for this other value of y, right? So different values of y, different slices of bread, different little, you might say, footprints for those little slices, and therefore different bounds for the range of values of x for the inside integral. No, that's the only difference. Main difference right there. Now, one thing you can also see from this picture is how the function will not be constant. So in particular, you can see that for a given value of y, it's this point right here that represents sort of, again, if you will, the x interval that we're going to be integrating over. This is the starting point for that x interval. That point is on this curve. And you can see that on that curve is where I will be able to solve for x as a function of y. Right? Given any y, there's a corresponding value of x. more algebraically, whatever the equation of this curve is. If you solve for x in that equation, that will tell you how this lower bound for x depends on y. In other words, it will give you explicitly this function, giving the lower bound for x as a function of y. Analogously, this point on this curve that has some equation that you can solve will then give you the upper bound for x. How we doing? Is everybody on board? Now, one thing I want to point out about this picture that I'm drawing, in order to find these bounds, right, notice that my entire picture, at least as is relevant to finding these bounds, all I need is here in the two-dimensional xy plane. I don't need the height stuff, right? This height's got nothing to do with these bounds. The height's just telling me what my integrand's going to be. That's what this f is right here. That's telling me the height. The bounds are determined entirely independently of what that f is. So since we don't need to understand f to understand the bounds, I don't need the z-axis. I don't need any of this vertical stuff in this picture at all. So really, my picture is more complicated than it needs to be. And rather than draw an unnecessarily challenging picture there, we can instead, let's see if I can do this artistically now. We can look at that same xy plane. We can again look at a value of y. We can think about this this y slice, or what's happening as we kind of try to compute that area under that curve. I can't see the area looking at it this way. I don't need to see the area. I know that the area is just an integral, right? All I need from this picture is to know, well, where's my lower bound, where's my upper bound? And I can see those right here, because the lower bound is still going to come from this point on this curve, which has some equation in which I can solve to get the bound that I'm interested in. And then likewise, for the upper bound, it's determined by that point. Now again, why this point? Well, this point because that's this point. This is the end of the little integral that I'm doing to compute that cross-sectional area. That point is where x is going to stop, and that point is on this curve, which again has some equation that I can then solve for x to get that upper bound. So rather than draw this picture here, this picture's hard, right? Look, it's all three-dimensional. It's tricky to draw these kinds of pictures. I'm pretty good at it, right? It's still challenging for me to do a decent job drawing these pictures. You can bypass that, right? You don't need to draw the three-dimensional picture. Just draw the domain, right? And let's see, let me get my colors straightened out here. When you're looking at a particular value for y, somewhere between c and d, on that y slice, to find the range of values of x, you identify the relevant points, you identify what curves they're on. Those curves will have some equations, solve for the appropriate variable. In this case, we're looking for x bounds, so in those equations we will solve for x, and that gives you your bounds. Nice, simple little process. Now let's dive into some examples. Okay, so this first example, I've got this written out in gory detail, more than I expect to actually see on work that y'all will submit. But I think it's good to have the first example be as clear as possible. So here's our domain. It's some triangle. We're being asked to compute this double integral right here. Now, quick pause. Why am I computing this double integral? Where'd that come from? Who knows? Doesn't matter. Could be anything, right? Maybe I'm interested in computing the amount of mass distributed over this region. Could be. Maybe I'm interested in computing the volume sitting over this region in R3 that I haven't drawn, don't want to draw. It's hard. right? Maybe I'm interested in computing the population. How many people are living in this little section of town, or what have you? Or maybe I want to compute the number of bacteria in this little region of the table. Whatever. Millions of different examples. Not what we're here for in this example. In this example, I just want to focus on how to turn a double integral, doesn't matter where it came from, into an iterated integral that we can crank out. Okay, so there's our domain. Now I'm going to do this two different ways. I'm going to start, no particular reason, I'm going to start with my differentials in this order right here. Dy dx. So we'll be doing our x slicing first, as it were. And then after we've done our x slicing, we'll do our y slicing. So, okay, diving in. Range of values for x. About like that. These points are all given. Coordinates over there. Pretty straightforward to see that x is going to start at 0. X is going to end at 1. We're going to have a bunch of x slices. Keep in mind an x slice is perpendicular to the x-axis. So there's our x slices, and the start and end, I think pretty clearly 0 to 1. So there's our outside bounds. Okay, now, per this picture up here, and keep in mind, all we're doing in these two-dimensional pictures is we're just kind of looking at the, satellite straight-down view of this picture. Right? So at this point, for my inside integral, don't lose sight of the fact that it's like I'm computing the cross-sectional area so that I can multiply by the thickness and, all that, right? So that's what's really going on, but what do I need to draw? Much less. All I need to draw is that for a given value of x, I need to look at the corresponding x slice. And there's my first value of y, right there. That's on this curve. That point is on this curve that has that equation. I'm seeing that straight from the picture, by the way. Right? So that's the starting point. It's on this curve. The equation is y equals 0. Take a pause at this moment to remind yourself, what are we doing with this equation? What's the purpose? Why am I interested in this? I'm interested in that because I'm looking for my range of values for y. I think it's really easy to lose track and accidentally solve for the wrong variable. You'd be surprised. I've done it myself, right? So I always take a pause, remind myself, oh yeah, I'm looking for my range of values for y. So I need to solve for y in that equation. And when you solve for y in that equation, you get 0. So that's your first y bound. In fact, let me draw this a little bit differently. Solving for y in this equation, I get that y as a function of x is just 0. This is a little bit of a weird sort of starting example. You can't see the x dependence, but that's fine. There's no problem. The x's don't have to be in there. The x's are just allowed to be in there. Okay, now let's look at the upper bound. The upper bound, where am I going to finish my, computing my cross-sectional area as I go up this x slice? I'm going to finish when I get to this point, right here, that point, which is on that curve, which I don't know the equation of immediately, but don't forget those points up there are given. You know these corners, right? These vertices, a little bit of quick algebra 1, you can find that that's the equation for that curve. Again, take a pause, right? Wait, what am I doing with that equation? Am I solving for x? Am I solving for y? Which one is it? Easy to get confused, get it around backwards. I'm looking for a range of values of y as I go up this x slice. So what I'm interested in solving for on this point, I'm interested in solving for y as a function of x. And so, just like there, how does y depend on x? Well, here's the formula for y as a function of x. Right there. Everybody good? All right. We'll slice it up in the other order momentarily. I do want to point out one little, slight twist. This is not really a big deal. But when you're evaluating this inside integral here, let's see here. You're going to do an antiderivative. Don't forget that for the purposes of the inside integral, y is your variable. X is a constant. You treat it like a constant. Don't integrate it incorrectly because you forgot what role which variable was playing, right? That's easy to mess up. The other weird thing is it feels strange to take a formula like x and plug that in as a value of y. It just feels kind of wrong. But that is, in fact, exactly what I'm going to do. I stick that formula, y as a function of x, into that y and into that y. And yes, it's a function, and yes, that's totally fine. All right, moving along. Same example. We're going to slice the other direction this time. Doesn't matter. Do it either way. Here, again, other order, dx, dy. That means y is our first variable. Our first slicing has y, you'll notice, going from 0 to 1. Again, these vertices are given. I see the nature of the shape. I can see how my y slices are going to kind of go like this. Right? Starting at 0, ending at 1. Again, we're going to fix a value of y. Let's say there. We're going to look at that y slice. And I'm going to do this a little bit more quickly because we already walked through super duper carefully last time. But our starting value for x is going to be at that point, which is on that curve, which has this equation. Taking the quick pause as usual. Wait a minute, what am I interested in about that? What should I solve for y? Should I solve for x? Easy to mess it up. I am looking for a bound of x as I now, for my inside integral, am moving in the x direction. So in that equation, looking as I am for an x bound, I solve for x as a function of y. That tells me my lower bound is y. Everybody good? Very importantly, not x. Y, because that's the formula for how to compute x as a function of y. Okay, and then analogously, last value for x is going to be at that point, which is on that curve, which has this It has this equation. Wait a minute again, I lost track. What am I computing here? I'm interested in finding my upper bound for x, so in that equation I need to solve for x. And I solve for x and get just 1. Everybody happy? Yeah.
Where did the inside of the integral x plus y come from?
Oh, yeah, so that was given. So in the statement of the question, we are computing this integral. Right, so this was just given in the statement of the question. Now, reasonable question, what does this have to do with a physical application? Well, again, there's a million physical applications, and maybe we're computing mass, and this is the mass per unit area. Or maybe we're computing total population, and this is the population density. Yeah, whatever. Yeah. Is that satisfying? Yeah. Okay. All right, so I've got a bunch more examples. This next example, the motivation is to try to learn a strategy for how to choose which way to slice. We've got these two different choices. I could slice either way. X on the outside or Y on the outside. Pros and cons. Please don't make a choice on the basis of, just geometrically I find it weird to slice in this order, so I'm always going to do this. or something like that, there are absolutely situations where that will get you into massive trouble. You do need to be able to do it either way. And you'll see the motivations for that in just a couple seconds. So what I'm going to do with this example, I'm going to first hit the highlights of where these bounds come from, with these two different choices of slicing order. I'm then going to address the question of, wait a minute, which one of these do we like better and why? And then I'm going to strategize as to what little morals did we learn from this experience that will help us decide which one of these slicing orders should I pick, depending on the particulars of the question. Okay, so starting off with slicing in that order, let's see, you see we are doing our x slices first. You see I've got x going from -2 to 2. Where'd that come from? Well, I'm interested in these 2 points, which are on, well, both of them are on that curve, and both of them are on this curve. So wait a second, if I want to understand, let's say, this upper bound point, right? This upper bound point comes where these 2 curves intersect. So I need to look at both of these equations, and with both of these equations in mind, solve for, wait a minute, what am I doing here? Oh yeah, I'm looking for x bounds, right? So in this pair of equations, I need to solve for x, and not much trouble. You can persuade yourself to get 2. Where things get a little confusing is when you look at the lower bound. Now this lower bound here comes from that point, and the thing is, it's on the same 2 curves. It's got the same 2 equations. Is this lower bound also 2? Of course not. What I want to make sure everybody remembers, and I know you know this, but it's very important to be reminded and be refreshed on this point, the squaring function is not invertible. Right? It's so tempting to look at this and solve for x and just say 2. Right? But it is not just 2. It could be 2 or -2. So when you're looking, for example, for this upper bound, you can't just say, oh, well, it's 2 because square root of 4 is 2. Not quite that simple. Square roots of 4 are both, it could be either 2 or -2. You then have to look at the picture, and from the picture decide, wait a minute, this upper bound that I'm looking for, I can see in the picture, hey, check it out, that value of x I'm looking for is clearly positive. That's why you pick the positive 2 for your upper bound. And then likewise, looking for this lower bound, you got to algebraically 2 and -2 to choose from. You pick the -2 because you can see in this picture that the lower bound you're looking for is clearly negative. That's why you pick the -2 for the lower bound. Is everybody okay with that? Okay. All right. Similar deal with slicing in the other order. If we're doing our y slicing first, then there you go. Y goes from 0 to 4. Here's what our y slices look like. And let's see here. For a given value of y, looking at that y slice, my lower bound is going to be determined by that point. My upper bound is going to be determined by that point. And again, the little weirdness that happens here is those are, again, both on the same curve. So the same little story happens again, a little bit slightly different, a little bit of a twist. It's not the outer bounds, but the inner bounds this time. That, again, we're solving for x because we're looking for the inside bounds here. X starts there, x ends there, going in the x direction. So again, tempting to solve for x and say it's square root of y. And it's not. It could be either. It could be plus, could be minus square root of y. And the picture tells you which is your upper and which is your lower. One of the big takeaways of this example is rely on the picture. The picture tells all. Algebra is a nice tool, but it is really hard in some cases to let the algebra tell you about some of the particulars that you really you really need the picture for. So please have a picture and rely on the picture. Okay, so that's the highlights of those two examples. Now let's decide which of these do you like better. I'm going to say I like this one better. The reason why is not because it's so wonderful, but mostly because this one I don't like. And I can tell you exactly why I don't like this integral down here. It's because if I look at the inside integral and I look at these bounds, I see there's square roots, and we don't like square roots. Now, I hear what you might be thinking. You might be thinking, oh, well, that's just in the bounds. The antiderivative of this, whatever this f is, the antiderivative of this f is what it is, independent of what this business about the bound. I'm just going to plug those in. Who cares? Right? And that's true. When it comes to computing this inside integral, the fact that these bounds are square roots is not a problem at all. And that's not what I'm worried about. What I'm worried about is the outside integral. If you look at this outside, the dy integral, all this stuff in blue is the integrand for my outside integral. And however decent and reasonable the x antiderivative might be, once you plug in these square roots, this blue integral itself, you would expect to have square roots in it. That means when you're doing the y integral, square root of y is going to be liberally peppered throughout your integrand. And that makes for a nasty integrand. Very often, as I'm sure y'all remember from Calc 1 and Calc 2. Everybody see what I'm doing there? So that's why I like the one on top better, is because, well, worst thing I can say about this is it's got a polynomial in it, but, could be worse, right? I mean, amongst categories of functions that I might have to deal with in my outside integral, polynomial is not the worst that I can imagine. I'd much rather have polynomials than logs, trigs, square roots, any of a number of other different nasty expressions. So this is not that bad. This one down here, pretty bad. Yes?
What would it f be, like, if you were going to fill it out?
Yeah, it depends on what the question is. So yeah, so again, the fact that I start with a double integral, and all I wanted to do here is focus on the process of turning a domain on a double integral into bounds on an iterated integral. And what the f is, it depends on your application. Maybe you're computing mass, and this is mass per unit area. Maybe you're computing population, that's population per unit area. Whatever. Yeah. So yeah, so I didn't want to give any specifics because that's just not what this example is about. Yeah. Okay, so we agree on which one is the good one and which one is the bad one. And now, how do we avoid the bad one? And roughly speaking, the point is this. Whichever variable that you put on the inside, that's the one you're going to need to solve for. Right? So I'm going to need to solve for y in that equation as I work this one out, because, well, it's the inside variable, and I'm going to that's one of the curves that my points are going to be on, in which I will need to solve for y. And I like solving for y in this equation. Partly because it's already been done for me, and that's nice, right? But that's not really the point. The point is, I get a prettier result solving for y in that equation. No square roots. And you see, right there, no square roots. Whereas, on the other hand, if I put x on the inside, I would need to solve for x in that equation. And that's why I get these square roots, which I don't like. So when you're trying to decide, which order should you do for the differentials, look at the algebra of your curves. Ask yourself very simply, within these equations, or whatever, which variable would I rather solve for? Which variable is going to give me a function that's easier to deal with in an eventual integral? And again, I think the choice is pretty clear here. Definitely don't want to solve for x because I don't like square roots. I'm not that unhappy about the idea of solving for y. Cool, I want to solve for y. Put y on the inside. All right. Okay, next example. Again, there's two different ways to slice. I'm going to do both. We'll, reap a little moral at the end. So starting with this order of the differentials, dx dy, you can see that y is going to kind of 0 to 1 with y slices that look like this. Yeah, everybody good? And then let's see here. For a given value of y, looking at that y slice, let me just focus on the curves. We can write down equations and stuff, right? But y'all can do that. The curves in question are that my lower bound is going to come from that point, which is on this curve. My upper bound is going to come from that point, which is on this curve. Okay, now details, y'all can take a look at that at your leisure. Okay, but roughly speaking, lower bound, let's see, well, upper bound, since I already have that color up, and lower bound. Okay. All right, now looking at this other option. Putting dx on the outside. Okay, x is going to go from 0 to 2, it would seem. My lower bound for my my x slices, right as I look at these x slices, my lower bound for y is going to come from this curve. My upper bound for y is going to come from that curve. Right? For any given value of x, my outside variable, as I go up in the y direction, I'll be going from green to blue. And you can already kind of see the problem. The problem here is this corner. That messes things up in a nasty way. I'd say, actually, let's phrase that a little differently. This is a symptom of a problem that is going to mess things up. Because if I look at this blue curve, I know I'm going to need to be solving for y. I'm going to need the equation of this blue curve. It has two equations. It's got one equation on the left side. It's got another equation on the right side. So because there's two equations, I have to kind of chop where those two curves intersect. In other words, at the corner, right? I have to chop the integral at the corner, and then I have to look at two totally separate integrals. Let me leave that corner highlighted there. For these values of x from 0 to 1, we're going to go from green to blue. No problem, perfectly simple equations. You can solve for y, nothing to it. And then for, let's see, color choices. Ooh, I'm out of colors. So for these values of x from 1 to 2, my y's are going to go from that curve to that curve. Right, so for the purple values of x, I go from light green to light blue. For the orange values of x, I go from dark green to dark blue. Different equation. Notice I get, likewise, different formulas for the upper y bounds. So that's why I end up with this nasty result, right? Now, again, let's take our pick here. We get to decide which way we're going to slice. It's up to us, whichever one you like better. I like this one up here better. It's only one integral. Here I'd have to do two separate integrals. that are going to be qualitatively different, right? I mean, when you do this inside integral, you're going to be plugging in the formula x wherever there are y's remaining. Whereas with this one on the right, looking at the inside integral, once you've done the antiderivative, I'll be plugging in a different function, 2 minus x, into wherever y's might remain. And so I will literally have 2 different dx integrals to compute. It is really a lot of extra work. Ballpark double the work. Everybody see what's going on there? So I have a real simple, just, kind of sifting through all of these details. The big moral walk away for me is try not to slice through a corner. Right? Ultimately, that's kind of what went wrong here. When I was slicing in the x direction, as I was going in that direction, here's my x slices, and right in the middle of my x range, I sliced through a corner. That's ultimately where the blame goes as to why I had to stop the integral I was working on, start a whole new integral, and finish up. Okay, so nice little rule of thumb to use. Try not to slice through corners. Does that make sense to everybody? Okay. All right. Okay, another example. Sometimes the domain is not explicitly given to you. Sometimes you have to kind of figure it out, how to find your domain. So, okay, here we have, you'll notice, a surface, namely this paraboloid given, and then another surface. Colors, come on, colors. Another surface, that's this plane, let's say, something like that. We're looking for the volume in between. That's what I have shaded in gray, now orange there. And before I get to the bounds and stuff, let's just think double integral for a minute. Looking at this part of the picture, here's the volume in question. Again, I'm going to think of this as a bunch of French fries, and I am going to argue that one French fry at a time, I can compute the volumes. The whole is the sum of the parts, right? It's basically a great big bowl of French fries. And on each one of those, I think it's actually pretty easy to compute that little differential volume, because the height there is the difference between these z coordinates. That's the height of my that's how tall that French fry is, right? And then let's see here, what's the area of the base down here? Well, there's a little area there at the sort of the bottom of the French fry, right? But of course, that's the same as the area of its shadow down here. That's just a little piece of my domain. So that's my dA. The volume is clearly height times the area of the base. So the double integral is pretty easy to derive. Cool, great, we did something. But looming question before us, what is the domain for this integral? Now, in the picture, you can see it. In the picture, you can see that my domain is this shadow. But algebraically, how do I represent that? How do I solve for it so that I can start playing our usual games and find the bounds? Okay, let me first show you the wrong move that a lot of people do. Let's see here. So, students reason correctly that I'm going to understand the domain by way of this kind of the perimeter of it. Sure. My domain's everything inside of that purple perimeter, right? Students argue correctly that that purple perimeter is the shadow of this curve right there. And students note correctly that that is where this paraboloid and this plane intersect. And because the points we're looking for, sitting in space, are where both of these surfaces intersect. They reason, still correct, by the way. They reason that, okay, well, I need to look at both of these equations. I need to find the x's and y's that satisfy both of those equations. All good so far. Here's where the students make the mistake. Students mistakenly think that if you want to solve a pair of equations, then they do this move that they invented that has no basis in real math called setting equations equal to each other. It's not a thing. That doesn't mean anything, right? So, in particular, what I have seen, I've seen this a million times. Students will set these to, for whatever reason, the right-hand side of one equation and the left-hand side of the other equation, and set those equal to each other, and then try to, go from there. And again, why? That doesn't make it. It's just. What does that have to do with the question? It doesn't actually make any sense. Now, let me try to first persuade you that setting equations equal to each other is just not a thing at all, right? So here we go. Here's a silly example. How would I find the values of x and y that permit both of these equations to be satisfied? If I want to know for which values of x and y is 3 equal to 3 and 7 equal to 7, do I need to find a way for 3 to equal to 7? No, of course not. That's ridiculous. It's just it's nonsense. Right? It's silly. Let me point out another silly, ridiculous aspect of this approach. When you have an equation, you can rewrite that equation lots of different ways. I could rewrite this equation here on the right, for example, as 4x plus 8y plus 2z minus 7 equals 0. Would I set this equal to that or this? Which one? Right? It doesn't make any sense. Okay, so here's the right way to do it, the reasonable way to do it. I am looking for certain values of x and y, such as that one. For any value of x and y, such as that one that I'm looking for, I can talk about how high do I have to go up to get onto the paraboloid. And it's going to be, that value of z right there. And I have an explicit formula for given this point, x and y, that tells me exactly how far I've got to go up to get onto the paraboloid. Okay, but likewise, I can reasonably ask, okay, from that same point, how high do I have to go up to get onto the plane? Well, I would go up to where I get onto the plane, and that point would have a z coordinate, and there it is. That says how high I have to go up to get onto the plane. So these are the two things that I want to be equal. If we're talking about a point that's actually on this intersection, then the height up to the paraboloid and the height up to the plane are the same, and so I want to set that equal to that. So I'm going to have to actually do a little bit of algebra here. Right? We're going to have to actually solve in this equation on the right. I'm going to have to solve for that z, which gives me this expression right here. That's the thing that I need to set equal to this z, namely this expression right here. Right? So I get this equation. And that's something that you can totally solve. Now, the actual solving of this equation, there's some algebraic mechanics in here. Y'all recall, I'm sure, that I've made this pitch. Don't forget that you need to know how to do completing the square. You got to know how to do completing the square. And that figures pretty prominently in this. You can see right here, I've got this x squared plus 2x. I need to be able to turn that into a square. And likewise, this business over here, I need to turn that into a square so that I can actually recognize what kind of an equation I have here. It's hard to tell from what's going on there, but it's easy to see here that this is just a circle. It's a circle centered at -1, -2. And the radius is some unfortunate number, square root of 17 half. That's weird, but whatever. Okay. Everybody good? Yeah.
Is there a reason you didn't just plug C into the other equation?
You can do that too. Yeah, that's equivalent. Yeah, sure. Totally fine. Yep. I just I like being able to make a persuasive geometric case for why I'm doing what I'm doing, right? And so you'd want to think through, okay, what's the argument that justifies doing that? Other than every time I've had two equations, I take one and I stick it into the other one, right? And so this has a nice, convenient geometric picture that's pretty hard to argue with, and so that's why I like this book. Yeah. Okay. So last thing, we have just now finished section 5.2, and in the remaining 4 minutes, we're going to finish section 5.3. Believe it or not, it's really quick. It's an oddly short section in the book. There's really only one discussion-worthy idea. Give it a read, right? Think it through, right? Of course. But here's the big idea. When you have an iterated integral, don't forget where the iterated integral came from. The iterated integral is just one point of view on a double integral. So here's why that can matter. Let's look at this expression right here, and you can see that the inside integral I would need to compute first is this right here. I would need to find an antiderivative of e to the x squared with respect to x, and you can't do that. And so there's a temptation to say, oh, well, I guess I'm out of luck. I guess I'll have to apply numerical methods or something like that. And that's a little premature, as it turns out. So let me show you the way we're actually going to compute this, and it's going to compute out analytically just fine, no problem. What we're going to do is recall, as I just noted, if I can get my thing to, yeah, okay, here we go, that my integral here is actually representative of a double integral. And there is a domain for my double integral. In some sense, all of these bounds here in this iterated integral, they came from slicing up this domain. And you can just see it right here in the formulas. It says right there, y is between 0 and 1. So, boom, this is what it looks like for y to be between 0 and 1. And then you can also see right here in these equations, you can see x starts at y. That's that curve. And you can see that x ends at 1. And that's that curve. Right, so for the given values of y and between these two curves, between the blue and the red and between these two values of y, there's your region, your green region. So sure, the question asked us to compute this iterated integral, but kind of working backwards, you can see that iterated integral is in fact no more than just, this double integral. So we've rephrased the question. The question was compute an iterated integral. The question is now compute this double integral. And having viewed it as a double integral, I am, of course, now free to slice it up however I want. Obviously, I'm not going to slice it the way it came to me. That wouldn't accomplish anything. So I'm going to slice it in the other order. X, pretty clearly 0 to 1. Right? Then for any given value of x, y starts at 0. Y ends at x. And now I've transformed the question again. Again, I started with an iterated integral. I reverse engineered a double integral. Now I've sliced the other way to make a different iterated integral. And believe it or not, it's all over but the shouting at this point. So looking at what we're left with here, right now there's a temptation to be discouraged by the fact that e to the x squared is still in there, right? But notice my first integral that I need to compute is of e to the x squared dy. And of course, x is a constant because x is the outside variable. And so that means if x is a constant, that actually means that this whole e to the, it's all a constant. And it integrates in a snap. Now, okay, well, yeah, but okay, here it is again. Now, here's that dx integral again, and we still have this e to the x squared. Still a little concerned, but now I have this extra factor of x. And this is not an undoable integral. This is a perfectly simple substitution. Just like u equals x squared goes through in a snap. So it's a slick move, very clever, right? And it's a cool example and all. That said, I do think it's a little weird to give this one example an entire section of the book. Anyway, give it a look. But I'm going to declare us done with 5.3 as well. We'll call it a day right there. Picking up with 5.4 on Wednesday. See you later.